Hey everyone, my name is Brianna Cody and I'm a physics major at PC. Today I'll be presenting on the research I've been working on this semester. This is a study on solar wind bulk flow velocity and the DST index pertaining to the human physiology. The outline of today's presentation will start off with what is space weather, where does it originate, and why does it matter? I'll then state our hypotheses and talk about what I did to start the research, ending with how I did my research and my conclusion, and some follow-up comments. So, what is space weather? When people think of when people think of weather, they think of something like rain or snow. But when you think of space, you don't really think of that. Well, in actuality, space has phenomena going on all the time, and it all starts at the sun. The reason for this is that the sun is constantly expelling massive amounts of energy, and that means it can hit Earth as well. This amount of energy can pretty much be simplified as space weather. More simply put, space weather is the effects of the sun and its actions on Earth, its atmosphere, and near-Earth space. One of the most common effects of space weather is the northern lights. Other phenomena can include the solar wind, solar flares, and space storms. Space storms in particular play an important role in the actions on Earth, as they can cause fluctuations in the Earth's magnetic field, which can cause phenomena at the ground. But why does this all matter? Well, technically, a few hundred years ago, it wouldn't have. But with technology advancing and people making more use of magnetic fields, electrical circuits, and pipelines, problems have occurred. Pretty much when space storms hit, they can affect these areas, causing power outages, eroding pipelines, and causing electrical systems to malfunction. But why doesn't this happen more often? Well, people have been able to learn how to mitigate some of the effects, and we have Earth's magnetic field. This shields us from a lot of the energy that the sun sends our way. But what happens when we don't have this? Well, that's a question we need to answer. Because if we're going to send people into space, like Mars or even further, we need to know the answer. Well, that's why we want to find out if there's any, that's why we'd like to find out if there's any effects on the human physiology due to space weather. That way we can better understand what'll happen when we're outside of the Earth's magnetic field. So, with that said, here are our hypotheses. We want to determine if there are solar wind variables that are strongly correlated to ground variables, because this will tell us if there's any possibility of there being an effect on the human physiology. We also want to determine if space weather affects the human physiology in certain rhythms. So, our data starts off with the Hallberg and Watanabe heart rate datasets. These are just heart rate measurements taken by two different people over separate time periods. We originally were going to use systolic and diastolic blood pressures, but decided to just focus on one physiological trait for now. From the Omni set, we decided to use the DST index, the bulk flow velocity, the magnitude of the average magnetic field vector, and the BZGSM. The DST index is a measurement of the fluctuation in the Earth's magnetic field. This variable plays an important role in defining the occurrence and severity of space storms. The bulk flow velocity is a measure of the plasma flow from the sun, and the magnitude of the average magnetic field vector is just the magnitude of the average measurement of the magnetic field. And the BZGSM stands for the Z direction of the geocentric solar magnetospheric system. Before I really started into the calculation side of the research, I wanted to learn more about what I was dealing with. To do this, I read through several articles and books, as well as created some code. One such code is an app. On screen, you can see a picture of this. I created it so that I could pick any time range from the datasets and only graph the data within those timelines. This came in really helpful because then I could, then I was able to just pick one of the Omni datasets and plot it against the heart rate or any of the other sets from the Hallberg and Watanabe sets. Using the app allowed me to make several observations over the course of my experimenting on it that I actually used later when I was doing the actual research. So, once I had a better understanding of what I was working with, we went ahead and processed the data. This included averaging places where multiple measurements had been taken at the same time and also making sure the data was in chronological order. We also discarded data points that seemed physiologically impossible. After this, we averaged the data by hour to have a common time interval, and then we were finally able to use MATLAB's timetable functions to create new data sets that contained only the necessary data from the Watanabe and Hallberg timelines. So, then after we had the data processed, we decided to narrow it down so it would be more manageable. To do this, we ran linear cross correlations on all of the omnisets, choosing the DST variable as our ground variable. This pretty much meant that it'd be our reference to the effects at Earth's surface. We then picked the top 3 most correlated data sets so they would be our solar variables. These turned out to be bulk flow, the average magnetic field vector, and BZ-GSM. The results that we found for the correlation coefficients on these are on screen. For bulk flow, we can see a moderate linear relationship to the DST index. But for average magnetic field vector and BZ-GSM, we only have a slight linear relationship to the DST index. Once we had our correlations, we went ahead and plotted the solar variables against the DST index. We plotted the Watanabe and Hallberg datasets separately because their timelines were separate and we wanted to simplify the process. The graphs on screen have a plot of the original data in blue, an average set of data in green, and a best fit line in red. The graph on screen currently is from the BZ-GSM variable. As you can see, there really doesn't seem to be much of a linear aspect to this plot. The next figure is the average magnetic field vector. This plot is slightly more linear, but still not ordered in much of a pattern. And the next plot is the highest correlated solar variable we had. This was the bulk flow variable. This variable appears more linear than both the previous graphs shown. So next we decided we wanted to see if there was any relationship with our physiological data and solar variables. We again ran linear cross correlations, switching DST for heart rate. You can see the results of these calculations in the table on screen. Both the Watanabe and Hallberg datasets returned very small correlation coefficients compared to the DST index. We then went ahead and plotted the solar variables against heart rate. Here you can see graphs similar to those previously mentioned. Again, they all contain a scatter plot of the original data, a line of the average data, and a line of best fit. On screen again is BZ-GSM. As you can see, the original data still doesn't seem to have much of a linear shape. The next graph is that of the average magnetic field vector. These plots also don't have much of a structure or linear order. And the last graph on screen is the bulk flow data, which shows only a slightly more linear aspect to its graph. After getting our correlation coefficients and their graphs, we decided to run a transform on the data. A more common method is the Fourier transform. This method breaks down complex inputs into sine and cosine waves, which allows us to make a better understanding on if there's a repetition within the signal. Another aspect of the transform is that it tends to run with consecutive data sets. Unfortunately, our data was not consecutive. You can see this with the picture up on screen. Thankfully, there are different types of transforms, so we were able to choose a different one. We ended up going with the Loam-Scargill analysis. This test works similarly, but it also uses non-consecutive data sets, such as the ones we worked with. On the next few slides, you can see our Loam-Scargill analysis graphs. This slide shows us a Loam-Scargill analysis of the Watanabe timeline. For the first 2 graphs, you can't really see anything significant within the frequencies. On the third graph, though, there seems to be very small peaks within the data. This could signify some sort of signal or rhythm. On this slide, you can see the Hallberg timeline Scargill analysis. Loam-Scargill analysis. Like the first and second graphs on the last one, there doesn't appear to be much of a, there doesn't seem to be much repetition within any of these signals. We also did a Lomscargle analysis on the heart rate data to confirm that there are rhythms within the human physiology. On both of these graphs, you can very clearly see definitive peaks. This, of course, most likely arises from some sort of circadian rhythm within the human physiology. So, now that we have our tests done, we're able to formulate a conclusion on the research. As for Hypothesis 1, we were not able to confirm any significant correlation between our physiological data sets and our solar variables beyond what we selected. As for Hypothesis 2, we know there's very clearly a 24-hour rhythm, but beyond that, our research still didn't find any significant rhythms related to space weather at this time. Even with these results, I feel that having access to larger data sets with more consistent measurements would have given us better options in determining if there were relationships between the human physiology and space weather. And if we could also have had a larger test group, I feel that would have filled in some of the gaps that were in the data, which could have biased our results. I also hope that maybe later we could be able to run different tests on the data to see if we missed anything with the tests that we actually did run. And as for further research, I think it would be nice to go back and see what exactly the slight peaks within the bulk flow data actually represented in one of the earlier graphs. Now that we've reached the end, here are the references I used. And I'd just like to take a moment to thank Dr. Wanless for his patience and his knowledge. I definitely wouldn't have been able to do as much without him working along with me. I'd also like to thank Dr. Owens and Dr. Roediger because they also gave me some recommendations and tips when I got confused. And finally, I'd love to thank my family for sitting with me through this editing and just keeping me going. And well, that's the end, and thank you for watching.